Here is something that will genuinely mess with your head. The massive container ships crossing the Pacific Ocean right now at this very moment are slower than ships from 1920. Not slightly slower, not a little behind. Slower in a way that should embarrass every engineer alive. And the wildest part is, the biggest shipping companies in the world looked at all their billion-dollar technology and said, slow down, on purpose. And that decision made them billions. But this is not a story about business strategy. This is a story about a physical law so ruthless, so mathematically cruel, that it has destroyed every single human attempt to fight it for over 150 years. Atomic ships, Soviet superweapons, underwater flying machines, the greatest engineers who ever lived all crashed into the same invisible wall. And today I am going to show you exactly what that wall is made of. Let us start with something simple. Imagine you are standing on the deck of the most powerful ocean liner ever built. Mid-20th century. North Atlantic. Thick fog everywhere. The furnaces below you are burning thousands of tons of coal every single hour. The turbines are screaming at their absolute limit. Engineers are soaked in sweat, pushing every lever as far as it will go. And the ship is going fast. Genuinely fast. The kind of fast that makes the whole hull vibrate and the plates on the dinner tables rattle. And then suddenly, nothing. The ship stops accelerating. Not because something broke. The engines are fine. There is actually plenty of power left inside them. In fact, the energy being used at that exact moment is enough to run 5 nuclear power stations simultaneously. But every single bit of that energy is just vanishing, disappearing into the ocean like it never existed. The ship is burning thousands of tons of coal just to maintain its speed, not to go faster, just to stay where it is on the speed dial. What is happening here is something called hull speed, and it is one of the most quietly devastating things in all of physics. When any ship moves through water, it pushes water out of the way at the front. That push creates a wave. Now here is the part that changes everything. The length of that wave depends directly on how fast the ship is going. Slow down and the wave is short. Speed up and the wave gets longer. Speed up more and it gets longer still. And at a certain critical speed, that wave becomes exactly as long as the ship itself. When that happens, the ship is sitting between its own bow wave at the front and its own stern wave at the back. It is trapped inside a valley of water that it made. The front of the ship is pointing uphill. The back is sinking down. To go any faster, the ship would have to physically climb over its own wave and start skimming on top of the water the way a small speedboat does. A speedboat weighing 1 ton can do that. It just needs a little more power and it pops up onto the surface and flies. A container ship weighing 300,000 tons cannot do that. To lift that much weight out of the water, you would need the energy output of 10 nuclear power stations working together at full capacity. It is not going to happen. It will never happen. The ship is locked inside its own wave forever at about 25 to 30 kilometers per hour. And no amount of engine power changes that equation. Now, imagine you are a naval engineer in 1900 and your brand new warship keeps mysteriously falling apart. Not the hull, not the engines, the propellers. You pull the ship out of the water for inspection, and what you see genuinely does not make sense. The propeller blades, made from some of the toughest bronze alloys available at the time, look like they have been chewed. Deep pits everywhere. Cracks running through solid metal. Some blades are just gone, snapped off completely, and this is happening after only 5 or 6 hours at full speed. You check the factories. You test the metal. You investigate every worker involved in manufacturing. Nothing. Every new ship, same problem. And the more powerful the engine you put on a ship, the faster the ocean eats the propellers. Captains were furious. Port workers were quietly convinced there was sabotage happening. Sailors started talking about metal cancer and the curse of deep water. Some scientists seriously suggested that seawater at high speeds transforms into something acidic and dissolves metal the way sugar dissolves in hot tea. Others thought the fast rotation of the propellers was generating electric discharges that burned holes in the blades. The real answer was so strange that nobody considered it for years. Tiny bubbles were doing it. This is called cavitation, and once you understand it, you cannot stop seeing it everywhere. Here is what actually happens. When a propeller spins very fast, it creates zones of extremely low pressure along the edges of the blades. And water has this interesting property where it does not actually need heat to boil. If the pressure drops low enough, water boils at normal temperature. So millions of microscopic steam bubbles form instantly along the spinning blade edges. Then those bubbles drift slightly to where the pressure is a little higher, and they collapse. They do not gently fizzle out. They implode. Each collapsing bubble releases a pressure spike of up to 400 atmospheres, focused into a space smaller than a grain of sand. That is a tiny explosion, detonating directly on the surface of your metal. Now multiply that by millions of bubbles, thousands of times per second, all hitting the same blade, every second of operation. That is not a chemical process. That is not electrical. That is a physical sandblasting so intense and so relentless that no material we have ever made can survive it forever. You can use better alloys, smarter blade shapes, more careful engineering. But you cannot make the bubbles stop. They are a consequence of speed itself. The faster you push the propeller, the more cavitation you get, the faster your propeller destroys itself. This is the second wall. Even if you somehow solved the wave problem, cavitation is waiting right behind it. But now, here is where the story gets genuinely extraordinary. Because in the 1970s, Soviet engineers did something that Western intelligence agencies refused to believe was real. They built a torpedo called the Shkval. When the first performance data was intercepted and analyzed in the West, the experts who read it assumed it was deliberate disinformation. A lie planted to confuse them, because the numbers were physically impossible. Water is 800 times denser than air. Trying to move faster than 100 kilometers per hour underwater is like trying to run through a wall of thick, wet concrete. Everything we have just talked about, the wave resistance, the cavitation, the pressure drag, all of it gets exponentially worse as you approach that kind of speed. And yet, the Shkval specifications showed a sustained speed of 370 kilometers per hour underwater. People who witnessed test launches described it as hearing a heavy rocket fire from beneath the ocean. A massive steel machine ripping out of the launch tube with a trail of boiling water that stayed visible and churning for several minutes after the target had already been destroyed. Western newspapers went wild with theories. Lasers vaporizing the water ahead of the torpedo. Ultrasonic emitters turning the sea into gas. People were designing transoceanic subway systems, imagining stepping onto a capsule in Murmansk and arriving in Havana 2 hours later. It felt like the ocean had finally been defeated. The actual explanation was both simpler and more limiting than anyone imagined. The Shkval used something called supercavitation. At the very nose of the torpedo sat a specially shaped disc. At high speed, that disc created such extreme low pressure that the water around the entire body of the torpedo vaporized instantly, not just at the blade edges like normal cavitation, everywhere. The whole torpedo was immediately surrounded by a continuous envelope of gas and steam. It was not moving through water. It was flying through a bubble it generated around itself. Only the very tip of the nose touched water. The rest of the body was in vapor, where resistance is almost non-existent. The Shkval was effectively a jet aircraft, just underground. And it worked. But here is what nobody mentions when they talk about how amazing this technology is. Maintaining that gas bubble requires a rocket engine that burns fuel so fast it would bankrupt any shipping company within days. The fuel consumption in 1 single minute of operation equals what a normal cargo ship uses in an entire day. You could not afford to carry anything on such a vessel. The fuel would cost more than whatever you were transporting. And then there is steering. You cannot meaningfully steer something inside a supercavitation bubble because your control surfaces are hanging in vapor. There is no water pushing against them. They are useless. If you try to turn sharply, the bubble breaks. And when the bubble collapses at that speed, the full force of the ocean hits the hull all at once. Hundreds of millions of tons of pressure arriving instantly. The torpedo is gone. Supercavitation was and remains a weapons technology. A single-use, unsteerable, extraordinarily expensive weapons technology. The physics gave an incredible gift with one hand and took away every practical application with the other. So what about just going around the problem entirely? What if instead of fighting the water, you simply leave it? In the 1960s, Soviet engineers built something that looked like it had been designed on another planet. The ekranoplan, a ground effect vehicle. An enormous winged machine that flew just 5 meters above the water's surface at 500 kilometers per hour. Western spy satellite analysts who first photographed the Caspian Sea monster, which is what they called it, thought they were looking at a crashed aircraft on the water. It was not crashed. It was operating perfectly. 500 kilometers per hour. 10 times faster than any cargo ship. Military planners started imagining entire armies crossing oceans in hours. It seemed like the solution everyone had been waiting for. It is not in service today. You have never ridden one. You never will. Because the ocean is not a smooth road. Waves in the open ocean during winter storms can reach 15 to 20 meters. And to use ground effect efficiently, the ekranoplan has to fly at 5 meters altitude. In a storm, those waves are 4 times taller than your flight path. At 500 kilometers per hour, hitting an ocean wave does not feel like a bump in the road. Structurally, it is identical to flying a commercial aircraft into the side of a building. The machine does not survive that. The same problem killed the hydrofoil dream. Hydrofoils are ships lifted above the water on underwater wings, like an airplane wing but pointing down. In calm harbors, they are genuinely beautiful machines, skimming the surface at 80 kilometers per hour. But the wings have to be light to generate lift, and light structures cannot take the relentless pounding of Atlantic swells for months at a time without fracturing. Every time engineers made them strong enough to survive the ocean, they became too heavy to lift the hull. Nature kept closing the door. And beneath all of these specific problems sits one mathematical law that connects all of them, and that nobody who romanticizes fast ships ever wants to hear. To go twice as fast in water, you do not need twice the engine power. You do not even need 4 times the power. You need 8 times the power. This is called the cube law of water resistance. Speed the ship up by 10% and fuel consumption doubles. That is not an approximation. That is the equation, exact and non-negotiable. Even if fuel were free, even if you had a nuclear reactor giving you unlimited energy, the structural stresses on the hull scale with speed the same way. The cavitation gets worse. The wave resistance gets worse. You are not just burning more fuel, you are destroying your own ship faster with every knot you add. The math is not something you engineer your way around. It is the physics of fluids, and it does not make exceptions. And so in 2008, one of the largest shipping companies in the world did something that made headlines everywhere. They told their captains to slow down. Formally, officially, permanently. The policy became known as slow steaming, and when the numbers came in, they were almost difficult to believe. Slowing down by just 10% reduced fuel consumption by close to 50%. Not 10% less fuel. Half. Because the cube law that punishes speed rewards slowness with equal and opposite force. Today, the biggest ships in the world travel at 20 to 25 kilometers per hour. Slower than a bicycle. Slower than steamships from 1920. And they are the most efficient cargo transportation system ever built in human history. One modern container ship moves 1 ton of goods 500 kilometers on a single liter of fuel. Nothing else comes close. No truck, no plane, no train. The entire century of trying to make ships faster, the record races, the atomic liner dreams, the torpedoes and ekranoplans and hydrofoils, all of it was humanity trying to bully the ocean into cooperating. And the breakthrough came when engineers finally stopped fighting and started working with the physics instead of against it. The ocean has rules: hull speed, cavitation, the cube law. These are not engineering problems waiting for a clever solution. They are the fundamental properties of water and physics, as permanent and unchangeable as gravity. The smartest thing the shipping industry ever did was accept that and optimize around it rather than waste another century ramming into it. Sometimes the most sophisticated thing you can build is the wisdom to stop building faster and start building smarter. The ocean does not care about your schedule, and the engineers who finally listened to it became the most successful ones of all.